Hello everyone. In this session, we are going to understand the Linux boot process step by step using this visual flow diagram. We'll start from the moment you press the power button, then see how the system enters BIOS or UEFI, loads the GRUB, starts the kernel, hands control to system D, and finally reaches the login screen. By the end of this session, you'll clearly understand what happens internally in Linux during boot and why each stage is important. So without wasting any time, let's start from very first stage, that is power on. What happens when you press the power button? The Linux boot process starts the moment you press the power button. Electricity reaches the motherboard, CPU, RAM, storage, and firmware chip. At this stage, the processor has no operating system loaded yet. It only knows one thing: begin executing instructions from a predefined memory location stored in the firmware. The firmware is either BIOS on older system or UEFI on modern machines. Its job is to initialize the hardware and prepare the system for loading an operating system. So the next step is BIOS or UEFI initialization. The firmware performs a post, that is power on self test. It checks whether essential hardware components are working correctly: RAM, CPU, keyboard controller, storage devices, display output, etc. Once the hardware passes these tests, the firmware searches for a bootable device based on the configured boot order. That is the next step. On BIOS system, it looks for the master boot record, also known as MBR. On UEFI system, it searches the EFI system partition for bootloader files. Next step is bootloader stage, that is GRUB. After firmware hands over the control, the bootloader takes over. In most Linux distributions, this bootloader is GRUB, that is Grand Unified Bootloader. GRUB loads the Linux kernel into the memory and may present a menu where users can choose between multiple kernels or operating system if the user is using dual boot. So next step is loading the kernel. It also passes important kernel parameters like debugging options or boot modes. Next, now the Linux kernel is loaded into the memory. The kernel is the core component of the operating system. It manages CPU scheduling, memory, devices, file systems, networking, and process control. Along with the kernel, GRUB also loads initramfs, that is initial RAM file system. This temporary file system contains essential drivers needed during early boot. Next stage is initramfs stage. Initramfs acts like a temporary workspace. It loads important kernel modules such as storage drivers, file system support, and decryption tools. Once the actual root file system is accessible, the system switches from initramfs to the real root file system using switch root. Now, the init system, that is system D, starts. After mounting the real root file system, the kernel launches the first user space, that is process, with the process ID PID1. On modern system, this is system D. This process is critical because all other processes and the services are started from it. The next step, the targets, services, and startup scripts. Now comes an important part: how services and scripts are actually executed. In system D, the concept of targets replaces the older run levels used in the traditional init system. A target is simply a group of services that define a system state. For example, multi-user.target represents a command line system. Graphical.target represents a full desktop environment. Each target contains multiple unit files. These unit files define services, mount points, devices, and more. Systemd reads these unit files and starts services based on the dependencies. For example, the network service will only start after required hardware and drivers are ready. Now, what about scripts? In older systems like sysvinit, booting relied heavily on shell scripts located in directories like etc init.d. These scripts were executed sequentially, but in systemd based systems, scripts are replaced by service unit files. However, systemd can still execute scripts when needed. For example, custom startup scripts can be added using systemd service files. Legacy scripts in etc init.d can still be supported. One major advantage of systemd is parallel execution. Instead of running scripts one by one, systemd starts multiple services at the same time whenever possible, making the boot process much faster. Next step, that is reaching the final state. Once all required services are started, the system reaches its target state. For servers, this is usually multi-user.target. For desktop system, it is graphical.target. At this stage, the system is full ready. We'll see either a terminal login prompt or a graphical login screen managed by display managers like GDM, LightDM, or SDDM. So, the Linux boot process is a chain of carefully connected layers. Firmware initializes hardware, GRUB loads the kernel mounts the root file system, systemd starts services and targets, and finally the user gets control. Just like peeling layers, each stage reveals the next until the system becomes full active. So, in this video, we discussed how the Linux boot process takes place step by step. We started from power on, understood BIOS or UEFI, saw how GRUB loads the kernel, how initramfs prepares the system, and how systemd uses targets, services, and scripts to complete the boot process. Thank you for watching. I hope this session helped you clearly understand the complete Linux boot sequence.